Desmos 2D is an awesome graphing calculator, being able to graph all sorts of functions, statistic stuff, parametric functions, polar equations, and whatever this thing is. It's even used in tests like the SAT. However, I did have one thing that I wanted to find the answer to. Can Desmos graph 3D equations? Well, it actually turns out Desmos did make a 3D graphing calculator, so that's it. Thank you for watching, please like and subscribe. In all seriousness, the goal of this project is to make a 3D graphing calculator within 2D Desmos and replicate as many of the features in actual Desmos 3D within our calculator. I decided to start off with the very basic parts of it, like the axes, before trying to do some weirder stuff and having to solve problems that arose, like rendering and coloring. If we load up a new Desmos 3D graph, the first thing we see is of course the X, Y, and Z axis, and also the XY plane and outline box, but we'll ignore these for now. We can also notice that we can change the view of the graph or rotate it. If we want to recreate this in 2D Desmos, we'll have to incorporate the view of the graph into how the axes look. Let's think about how to represent a view of the graph and how the axes would look. In Desmos 3D, by dragging left and right, we basically change the horizontal angle of the view, and by dragging up and down, we change the vertical angle of the view. This is exactly what spherical coordinates do. We use two angles, theta and phi, to represent the direction that the viewer looks in. Theta in this case is the horizontal angle operating on the XY plane, and phi is the vertical angle that is taken with respect to the z-axis. However, just because we know which angles to use doesn't mean we know how to make the three axes. Even though the lengths of the axes in 3D space stay the same, if you want to recreate the axes on a purely 2D space on Desmos 2D, they would actually have to take on different lengths, and weird directions that all depend on theta and phi somehow. One thing to start with is the length of the z-axis. On Desmos 3D, we see that if we rotate the graph horizontally or change theta, the z-axis, both in terms of length and direction, stays constant. It only changes in length if we get a different value of phi. If phi is 0, or we're looking directly down our graph, we see that the length of the z-axis is 0. If phi is pi over 2, or we're looking horizontally, the z-axis reaches its full or actual length. It makes sense that the z-axis's length would then correspond to sine of phi. The z-axis is always vertical, so we can represent the z-axis as this parametric function. Next, we can think about the x and y axes. If z is related to sine of phi, we can naturally predict that the x and y axes are related to cosine of phi. And indeed, we can see that in Desmos 3D, if phi is 0, the x and y axes reach their maximum lengths, but if phi is pi over 2, the x and y axes have their minimum lengths. We can figure out how much cosine phi is related to the x and y axes by looking at the ellipse that the two axes exist on. This sounds kind of complicated, but we just have to notice that if we keep phi constant and change theta, the x and y axes are parts of an ellipse. The horizontal axis of this ellipse is always constant, regardless of phi, but the vertical axis changes with respect to phi. We see that specifically, the vertical axis of the ellipse is proportional to cosine of phi. Using this, we can come up with these two equations. The cosine theta and sine theta allow the x and y axes to change as theta changes. Our final product for the axes is this. Since we can now graph the directions the axes point toward, we can start graphing points. Right now, the lengths of the axes are 8 in the 3D space, so we can keep that in mind when we graph points. Imagine trying to graph by hand a 3-dimensional point. For example, to graph 2, 1, 1, we would have to first move 2 units in the x direction, then 1 in the y direction, and finally a unit in the z direction. In our calculator, we can do something similar. To graph 2, 1, 1, we tell the calculator to graph a point by moving 2 in the x direction, 1 in the y direction, and 1 in the z direction. In other words, we can create the 3 basis vectors I hat, j hat, and k hat. This allows us to graph not just points, but also single variable vector functions. For example, we can graph a line, this sine wave with this equation, or this spiral with this equation. Creating these basis vectors was a crucial part of the graphing calculator. We'll now be able to create more features with them, including surfaces. But for now, we'll have to deal with scaling. Right now, all of the axes have lengths 8 in the 3D world. However, technically, we should be able to change these lengths, as is possible in Desmos 3D. Desmos 3D is advanced enough to let us even shift around the graph rather than just to zoom around the origin, but I didn't really want to go that far in. Just a simple scaling system would be fine. In Desmos 3D, zooming in and out doesn't actually change the sizes of the axes. Rather, it just kind of shrinks or expands everything that's being graphed. In other words, the representations of I hat, j hat, and k hat are what's really changing. By tweaking the basis vectors, we can create a rudimentary scaling system, where the lengths of the axes are c subscale. We can also add a scale controller on the interface of the graph. Now we get to the problem of graphing surfaces, specifically 2 variable functions. The easiest way to graph them, I figured, would be to basically graph a bunch of slices of them. First with constant x values, and then constant y values. This creates a basic but still a very much functional representation of a surface. In addition, I added controls for how many slices or traces of the graph get shown, represented by the variable n subslices. Although this looks good, I wanted to try doing something more complicated. Right now, the graph is basically a net, but if we want the full features of Desmos 3D, we should really be seeing a filled-in surface. However, graphing a surface this way of course poses many challenges. For one, it wouldn't be just the same color throughout. Different places on the surface would have different colors depending on the light source and the angle between the viewer and the part of the graph. In other words, we need some sort of light mechanic. My first idea was to basically layer a bunch of shapes, as if we are drawing the graph. For example, if our graph was a semicircle, we could first layer the darkest color, and then layer colors that are lighter. However, I figured this would be pretty hard to graph with Desmos 2D's capabilities, so I decided to go a different way. Before we get to graphing functions, we first need to consider how shading works. Consider just a sphere with a single light source, that is far away enough that its rays are essentially parallel, like the sun but not a desk lamp. There are some areas that are bright, where the most of the light from the light source is being reflected by the surface, and also some areas that are dark, where the least amount of light gets reflected to the viewer. Other areas are sort of in between. One important thing to note is that if the viewer changes their position, as in the angle they're looking at, the shading of the surface changes. For some materials, this is hard to see because they scatter light a lot, but for more reflective materials, this is more obvious. The best way to understand what is going on might be to deal with a plane. As the plane rotates, its color changes because it reflects a different amount of light to the viewer. Theoretically, it should reflect the most light when it points exactly in between the direction of the light source and the direction towards the viewer, when its normal vector bisects the angle between the light source and the viewer. If the normal vector were slightly off, then it would reflect a bit less light. And if the surface was pointing completely away, then it would reflect the least amount of light. Using Desmos' custom color capabilities, I came up with this color function. Given the angle between the normal vector and the optimized angle, which ranges from 0 to pi, it outputs a color. The smaller the angle, the lighter it is. However, we still need a way to calculate the angle that a part of the surface has with respect to the viewer. For this, I basically utilized the dot product between the normal vector at a point and the optimized angle and the inverse cosine. With all this in mind, we can now graph a surface with shading. Although this is great, there are a few problems. First off, because of how Desmos 2D renders things, the function is always in front of the 3 axes, regardless of how we're viewing things. For this, I'd have to create some adaptive system that could layer things. Furthermore, the graph is rendered with the x term always being constant, basically a bunch of curves with constant x values. This is bad for the shader mechanism I made, because each curve or section that Desmos makes has the same color throughout, and so it really shades based off of just one point. This is especially noticeable if you get to view the graph at a certain angle. In the longest part of this project, I would have to grapple with all of these problems and new ones that popped up. The first thing I did was to deal with layering the surface and the axes. Initially, I was thinking of maybe telling the x, y, z axes to only graph depending on whether the function crossed it or not, but that turned out to be way too hard. Eventually, I made a system where different parts of the graph would be rendered individually. This included parts above the xy plane, parts below the xy plane, parts behind the z-axis, and parts in front of the z-axis. This was kind of annoying to do, since now the graph had 5 separate renderings, but things would get a lot worse. Here, I tried to fix how from certain angles, the graph looks like it has a single color. To fix this, I basically doubled the number of renderings. For some viewing angles, the graph would be rendered with constant x values, and for other viewing angles, the graph would be rendered with constant y values. Furthermore, while doing this, I realized that if a function is linear with respect to one variable, it could also end up looking like it is just one color. To deal with this, I basically made a detector for whether or not a function is linear with respect to one variable by using second-order partial derivatives. Overall, this update quadrupled the number of renderings from 5 to 20. In addition, the detector I made was very unstable, and I would have to overcome that. I decided to try to fix the detector. The way I achieved this was by making randomized points x, y, taking first-order partial derivatives from these points, and then taking their standard deviation. If the graphs were linear with respect to x, then all the partial derivative values would be the same, so their standard deviation would be 0. If the function were not linear, because the points are randomized, the standard deviation would be above 0. The detector worked very well in tests, but it had one major flaw: functions with limited domains. For example, square root x only works for non-negative x values, and because Desmos sets their derivative values as undefined, none of the renderings would actually show. I would have to fix this in later updates. Despite Desmos' shortcomings, I managed to make a system that would make all the undefined derivative values be 0. This way, the standard deviation would actually be able to be calculated and not tweak out. Eventually, this system would allow graphs like square root x to be shown. In version 6.7, I also added a more functional border system. The gray outlines of the cube are layered properly now. I finally finished troubleshooting by basically experimenting around with different graphs. There were a lot of rendering issues. Sometimes graphs would look inverted and have weird colorings, and etc. This required making 2 variables called fRenderRegressor1 and fRenderRegressor2. This part took a very long time to do properly, since it was less thinking and just trying to find every possible error. By this point, I had over 25 separate renderings of the surface. I fixed most of the rendering issues, but I did have to fix some more issues time to time, since there were more than 25 different renderings and any one of them could be having problems without me knowing. Up until this point, I only had orange for the color function, but Desmos 3D offers a few more colors than just that. So I began making red, green, blue, purple, and gray color functions. In addition, I fixed even more rendering problems. At one point, I tried to change the rendering system by making it more detailed, but eventually gave up on it because it created a lot of issues and also didn't implement properly. In this system, I basically tried to render each curve that makes up the surface in separate chunks with different colors. Previously, the graph always had the same color along lines, but technically, it would be better if this didn't happen. However, this made a lot of things tweak out, so I didn't keep it. With the finished color functions, I decided to make a color changer UI. By dragging points into one of the circles, the graph's color can change. Another detail on Desmos 3D that I wanted to remake was the XY plane. In addition to the gray translucent plane, Desmos 3D also has grid lines for the plane that change depending on the scale of the graph. I made good use of the floor function to make this scaling system, which includes the minor guidelines and the major grid lines. In addition, I made some controls for the opacity of the whole XY plane, along with switches for the grid lines. At this point, I completed most things I wanted to try to make. Although there were a few more features I wished I could have made, I realized that they would be very complicated with Desmos 2D's limits. Overall, this project was extremely painful to work with. There were so many problems that arose, especially from the multivariable function calculator, that took a lot of mindless troubleshooting to get through. It sometimes felt like I was going in circles with all the fixing I had to do. The calculator is also extremely laggy since it has to graph around 50 to 400 separate curves from almost 30 different equations, each one having a crazy number of conditions. Take a look at this, for example. Some conditions are about the viewing angles, 2 of the conditions are for staying within the black square viewing port, others are for staying within the gray cube, and so on. The worst part is that, well, this could have been a lot worse if I decided to incorporate the more advanced shading system, where each curve would be broken down into segments with different colors. This would increase the number of curves to probably like up to 20,000, at which point I'm positive Desmos would just crash. There of course are some things that I thought about adding but couldn't. For example, a cool feature on Desmos 3D is the perspective feature. The graph can change from an orthogonal view to perspective views with varying amounts of distortion. For this, I thought of a completely different rendering system that also overhauls the whole layering system. Instead of graphing traces of a surface that run parallel to the x or y axes, I instead thought of a concentric sphere system, where a bunch of slices along spheres of different sizes are taken. This would easily integrate a perspective control system, since I could basically change the centers of the spheres. In addition, this system would have a built-in layering system. Slices with further away spheres are always behind slices with closer spheres. However, this system would require a lot of work and might not even work with Desmos' limitations, so I have yet to implement it. Another thing I thought of adding are 2 variable 3-dimensional vector valued functions. In other words, parametric surfaces. In the 2D world, this would basically be like going from normal single variable functions to parametric functions. It will be a nightmare at best to come up with a system that would shade such surfaces, so I decided to let go of this. In conclusion, this is a lot of math that I had to go through. On one hand, it required a lot of thinking and essentially engineering, but on the other hand, this is basically coding but worse, because the only person who can understand what is going on here is me. But it's even worse because when I go back, I can't fully understand what I did. I kind of have to poke around that stuff until something works out. And even then, the issues keep popping up everywhere. This is 0 out of 10 experience, would not recommend, and I hope no one else goes down this hellhole. Thanks for watching.